Good afternoon. So we finally reached the last topic that I want to cover in this class. There's more obviously on polar coordinates, but the only thing I want to cover before we close the books on Calculus 2 is one calculus application of polar coordinates, which is the areas. How do we compute areas in polar coordinates? If you think about it, in terms of integration, application of integrations, the computation of area was like the first application. It was essentially used as a way to construct the Riemann integral in Calculus 1, if you remember. So I'd like to do the same for curves represented in polar coordinates. And as you move along with other topics in other math courses, you will see more applications that can be translated in polar coordinates. So so take a moment obviously to sketch this picture. This application, the computation of the areas in polar coordinates that I want to cover, is for a region that follows this type of boundary. I mean, the region defined in the following way. First of all, one boundary, this curve here between this angle, given in polar coordinates as a function of theta. So again, this portion of the region here, and then bounded by the by A and B for the theta, for the domain, for the polar angle. Now remember how I measure this, right? So this can be in any quadrant, but for simplicity, we look at the first quadrant here, right? So the lower bound for theta means all the points above this line here, assuming that this is A, this angle here from the positive semi-axis. And the upper bound for theta represents this side of the angle. So again, imagine that this is equal to B, that angle measured with the positive semi-axis. So essentially the region I'm talking about is bounded by three borders, if you want. Two of them are given by the bounds of theta, and the other one is given by a function r in terms of theta. So, and I want to compute the area, right? So the goal is to find this area. So this is the analogous of essentially finding the area of a function under the graph, right, in Cartesian coordinates, except that the geometric meaning is completely different now when you look at the meaning of the geometric meaning of the bounds for theta and then the function itself. So how do we compute this area? Well, the idea is actually not that complicated. Again, it's just a matter of interpreting the geometry of all that happens here. So let me remind you or remark that if you have a full circle, there is a formula for the area of the so-called circular sector. So let's say this is the radius r, and let's say we have here a circular sector of a circle of angle theta. Right, so theta is the angle between the two radii. I should make this picture maybe bigger here, right? So this is a full circle, and let's say this is theta, and the radius is r. So there's a formula from the geometry that states the area of this piece of the circular sector is equal to 1/2 r squared times theta. Again, theta is measured in radians. Now, you remember that the full area of a circle is pi r squared. So this is where it comes from, right? I mean, if you have a full circle, the area is, the theta is 2 pi, right, for a full circle. So this gives you, I hope, the familiar pi r squared, right, which most people know, the area of a circle. Just a sector of a circle, or a segment of a circle, I think it's called sometimes, it's r squared over 2 times theta, the angle between the two radii that, bound or border that circular sector. Now it's important to understand that what you have in the picture here on the left, it's not actually a circular sector, right? Because the curve r equals f of theta could be any curve, doesn't have to be a circle. But the reason I'm making this detour with a segment of a circle is because look what happens if you do the partition of theta as you normally do for any Riemann integral, right? So I mean, remember, you construct the Riemann integral by making a partition of the interval domain, right? So for each piece of the partition, you're looking basically at a narrow distance between two nearby points on the partition, which we can denote it by d theta, as we represented by dx in the case of Cartesian coordinates. But d theta here is basically a small change in the angle theta. So a partition on the theta, on the domain for theta, results in a partition of the entire area that I try to compute into thin strips like this in an angular shape, basically. So each of them is essentially a very thin or acute angle. So for instance, a typical one, exaggerating the distance here, of course, corresponding to one partition of theta, will look like that, right? So this basically will be d theta, right? The distance between two of those radii corresponding to this partition. So if you imagine that this partition is very fine, that the distance is very small, each of these pieces, let me emphasize, for example, typical one here. Each of these pieces can be approximated, if I were to sketch it here in an exaggerated shape, imagine if you zoom it out, can be approximated by a thin circular sector. And because this is so small, the angle between these two radii, d theta, is so small, then you can think of the same r essentially, right, for those two sides of that angle. So this is the stuff that you actually integrate over to add up so you can come up with the full formula for the surface of this region. Essentially, in calculus 1 for Cartesian coordinates, you overlap the region with rectangles. Here you overlap the region by thin circular sectors and you integrate over them. This is of course a very rough explanation because I don't want to bother with taking the Riemann sums and doing all those limits and all that kind of stuff. The only difference, again, I want to focus on is the shape of the piece you integrate over. That shape is the area of a circular sector. And for that reason, the full area of this region, the formula for the area, will be the integral over the domain for theta, which is AB in my formula, and the formula for the area of a circular sector, 1/2 the radius to the power 2 as a function of theta, d theta. So if you want, you can write it like that. The integral from A to B, 1/2 f of theta to the power 2 d theta. So that's the formula for the area of that region in polar coordinates. Again, it's important to remember that f of theta is essentially the radius, the polar radius in terms of theta. So we're gonna finish, I'll continue with 2 examples and I'll say some final remarks and that'll be it. So stay tuned. Alright, so let's take a look at this example. By the way, the way to sketch it, don't worry too much about it. You could figure out if you really try and plug in lots of numbers to have an idea that this is indeed how it looks like, but you can simply use a computer to actually sketch it so that you don't have to bother too much with doing this by hand. So this is kind of like 2 teardrops opposite to each other, and that the equation of this picture here will be r squared equals sine of 2 theta. Now let's say I want to find the area of half of it. So in that case, obviously you can take r to be positive, which is square root of sine of 2 theta. And the reason, by the way, it's gonna be the full picture looks like these 2 opposite teardrops is because normally when you take the square root, you have plus minus square root of sine of 2 theta. So for each point you have the opposite one with the negative r. But let's say I want to focus only on the one in the first quadrant with a positive r. Now, in terms of the, my picture is not really that great here actually, because this is kind of tangent to the axis. So the domain is also given. So the actual domain for this piece, for theta, is actually 0 and pi over 2. So actually it's going to be tangent essentially. It starts from the point 0, 0, and then it increases, and then it goes all the way back to 0. If you think about it, there's a maximum radius, because if theta is between 0 and pi over 2, 2 theta is between 0 and pi, right? So at the extremes, sine of that is 0. Sine of 0 is 0. Sine of pi is 0. And in between, there's a maximum when sine is going to be equal to 1, right? Corresponding to basically for theta pi over 4 basically, right? The in between. Yeah, when theta is pi over 4. And now let's find the area, right, with the formula, right? So the formula is the integral from 0 to pi over 2, 1/2 the radius to the power 2. The radius is square root of sine of 2 theta to the power 2. And from this point on, you just integrate with however technique of integration is suitable. Now, this is just a simple u substitution. The integral of sine of 2 theta is minus 1/2 cosine of 2 theta. So it's minus 1 over 4 cosine of 2 theta between 0 and pi over 2. Plug in. I don't have room here, so plug in pi over 2 and then 0. Now cosine of pi is minus 1 and this cosine of 0 is 1, so that's going to be plus 1 over 4. So 1 over 4 plus 1 over 4, that's going to be 1 over 2. So that's the area of that teardrop. Let's do another one. Let's see if I have the figure for this one to show you. So let's say r is equal to, you don't actually need to sketch the picture, but just to have an idea how it looks like, 2 plus cosine of theta. So r equals 2 plus cosine of theta. And let's see, the domain is pi over 2 and pi. This looks like kind of like forest circle on the left. So if you generate this picture, the I can do that easily by hand. We can do this in Maple actually in the labs maybe. This piece over here for the domain given in the picture, right? So r plus 2 r equals 2 plus cosine of theta is this full curve, but restricted to pi over 2 and pi is going to be this, right? So pi over 2 is going to be this. So this is theta equals pi over 2, the lower bound. And over here, theta is going to be pi, the upper bound. And then this is the curve, 2 plus cosine of theta, which borders the other piece of the region. And of course, the formula is the same. So the area is going to be the integral from pi over 2 to pi, 1 over 2 radius to the power 2 in terms of theta. And here we have to expand and do some algebra. And this basically ends up, as typically does with many applications in polar coordinates, is going to end up a trigonometric integral for which you have to use what you learn from trigonometric integrals. So let's see if I expand this, that's going to be 4 plus 4 cosine of theta plus cosine squared of theta. Now, cosine squared is an even power of cosine, so you need to use the double angle formula. Which means cosine squared is replaced by 1/2 plus 1/2 cosine of 2 theta. And let's simplify and clean up a little bit before we integrate, because now we can integrate term by term. But let's see, I have 4 plus 1/2, which combines into 9/2 times the external 1/2, that makes it 9/4. Then 4 cosine over 2, that's 2 cosine. And then 1/4 cosine of 2 theta. And now we can integrate 9/4 theta plus 2 sine of theta plus 1/4, and the integral of cosine of 2 theta is like a u substitution. It's 1/2 sine of 2 theta between pi/3 and pi. And let's put some parentheses here. So 9, plug in pi, right? 9 pi/4, 2 sine of pi, and 1/8 sine of 2 pi. And then here 9/4 times pi/2 plus 2 sine of pi/2, and then plus 1/8 sine of 2 theta, which is makes it sine of pi. All right, so sine of pi is 0, sine of 2 pi is 0, this is 0, sine of pi/2 is 1, so I'm left with 9 pi/4 minus 9 pi/8 minus 2. This combines to 9 pi/8 and then minus 2. Okay, so I think that's it. I don't know, well, maybe I'll make later on, maybe final remarks on a separate video. If you manage to get it up until this point, as always, if you notice any typos or anything like that, or any remarks, you can leave it in a comment, and I might revisit some of these and curate them if I have the time later, or maybe add topics later. Usually when I revisit a list like this, I typically add extra topics which essentially are non-mandatory for the course, just for general interest, but those will be labeled accordingly so that you know you can skip them if you want to just follow all the lessons from top to finish, and not the non-mandatory ones, so to speak. So I really hope you enjoyed it, and I'll see you next time.